Video, we discuss about a special class of random process known as Gaussian process. We need to study Gaussian process. There are two reasons. Firstly, the random processes produced by most of the physical phenomena can be understood by applying Gaussian model. Secondly, the mathematical analysis of Gaussian processes is easy. It involves exponential functions. Therefore, the mathematical analysis of Gaussian process is relatively easy. And these processes are very important in the study of communication systems. For understanding Gaussian random process, we study about jointly Gaussian random variables. Suppose if I consider a set of random variables such as W1, W2, dash dash dash, say Wm. These are a set of random variables which are assumed to be normal IID random variables. IID means independent and identically distributed random variable. What does it mean? If I say the random variables are IID random variable, that is independent and identically distributed random variable, it means the probability distribution function is similar for each trial of the experiment. Now, if you take one set of these random variables, that is the linear combination of these random variables, that gives us the Gaussian random variable Z1. So the linear combination, that is A11 W1 plus A12 W2 plus dash dash plus A1M Wm. All these coefficients A11, A12 and A1M are known as the coefficients. So the linear combination of these random variables will give us a Gaussian random variable. Similarly, the second set of linear combination will give us Z2 and so on, and finally the Zn is nth linear combination of the random variables. Now in this scenario, the Z1, Z2 and Zn are known as jointly Gaussian random variables. In the previous slide, we have seen various linear combinations of random variables. If you put it in a simple form, we can write it as Z is equal to AW. If you expand this in the matrix form, the Z contains a column matrix of the elements Z1, Z2 up to Zn, and we have A is a n by m matrix. There are n rows and m columns here, and then we have another column matrix W1, W2 up to Wm, which is a set of random variables. So the simple equation Z is equal to AW can be expanded in the matrix form this way. Now the first column matrix consists of all jointly Gaussian random variables, and the second one, the matrix A, contains all coefficients, and W matrix contains the combination of random variables. So now this vector containing the elements of Gaussian random variables is known as Gaussian random vector. Consider the covariance of Gaussian random vector. The covariance is indicated as Kz, and it is given as expectation of Z into Z transpose. As Z is a matrix, the matrix multiplication involves Z and transpose of Z. And we already know that Z is equal to A into W. Now substitute this into the definition of covariance, and rearranging the words we get this. Now here we are assuming that all these random variables W1, W2, dash dash Wm are normal and statistically independent. So we know in the normal and statistically independent case, the mean value is 0, variance is 1, and the statistically independent means Exy is equal to Ex into Ey. Therefore, if I take the product of W, W transpose and rearranging and applying the condition of normal and statistical independent variable, then that reduces to unit matrix. Therefore, the covariance of a Gaussian random vector reduces to the multiplication of quotient matrix and its transpose. It turns out to be very simple. Now we define Gaussian random process. If you consider any random process and all its samples are jointly Gaussian random variables, in that case, that random process is known as Gaussian process. So the samples of the Gaussian process are jointly Gaussian random variables. Now this is of great interest for us in communication systems because the noise is Gaussian process. Now the Gaussian process consists of so many Gaussian random variables, then its joint PDF is the product of individual marginal PDFs. That is pi is equal to pi in pi I is equal to 1 to m of zi, and this is PDF of single Gaussian random variable. So if we take the mean value as 0, 0 mean Gaussian random variable, then each PDF is given as 1 by root 2 pi sigma I square e power minus zi square by 2 sigma I square. This is Gaussian PDF with 0 mean. Now we discuss the alternate definition of Gaussian random process. We take y is equal to integral 0 to t gt xt dt, where gt is a function, a deterministic function, xt is a random process. Y is under the integral the product of gt and xt. So y is a linear function of xt. If each linear function of xt leads to a Gaussian random variable, that is the combination of gt and xt is giving y as a Gaussian random variable, then the process xt is known as Gaussian random process. So if each linear functional of xt is giving us Gaussian random variable, and the process xt is known as Gaussian random process. This is alternate definition of Gaussian random process. Now I rewrite the equation for the Gaussian process, that is y is equal to integral 0 to t gt xt dt, where gt is a function, deterministic function, xt is a random process. If each linear function leads to a Gaussian random variable y, then the process xt is known as Gaussian process, that we have seen in the previous slide. Now if the y is Gaussian distributed random variable, then it is given as the PDF of y is given as fy is equal to 1 by root 2 pi sigma square y e power minus x minus mu y square by 2 sigma square y. In this equation, this is the PDF of Gaussian random variable, and in this equation mu y is the mean of random variable and sigma square y is the variance of random variable. Now in this particular Gaussian PDF, if I substitute mean as equal to 0 and variance sigma square y is equal to 1, then substituting these values, this equation reduces to the simple form fy is equal to 1 by root 2 pi e power minus y square by 2. This is known as normalized Gaussian distribution, where the mean value is equal to 0 and variance is 1. It is also indicated as capital N 01. In certain books, the notation is given as N01, where 0 indicates the mean value 0, variance is 1, and it is normalized. I rewrite the equation for normalized Gaussian distribution, that is PDF of normalized Gaussian distribution f capital Y, y is equal to 1 by root 2 pi exponential minus y square by 2. This is the PDF of normalized Gaussian distribution. And if you draw it, the diagram looks like this, in which mean value is 0 and variance is 1. So this is the diagram of normalized Gaussian distribution. We discuss the more famous central limit theorem. First we consider the set of random variables xi, where I is equal to 1, 2, dash dash n. Now xi constitutes a set of random variables and they are assumed to be IID. As you have seen in the previous slides, IID stands for independently and identically distributed random variable. So what does it mean? Independently and identically distributed. It means they are statistically independent. All random variables in Xi are statistically independent and they have the same probability distribution. All random variables in Xi have same probability distribution with mu x as mean and sigma square x as variance. Now, if these random variables are normalized with respect to variance, then we write an equation yi is equal to 1 by sigma x xi minus dx. So now y constitutes the normalized IID random variables. It constitutes the set of normalized IID random variables, and for this the mean value is 0, EYI is equal to 0 and variance yi is equal to 1. Now having defined the normalized IID random variables, we now go for central limit theorem. Consider the equation Vn is equal to 1 by root n sigma I is equal to 1 to n yi. What is yi? Yi is normalized IID random variables that we have seen in the previous slide. So Vn is the linear combination of yi. Now as per central limit theorem, the linear combination of normalized IID random variable leads to Gaussian distribution if n approaches to infinity. It means if you combine the IID random variables, normally distributed IID random variables, then it leads to Gaussian distribution provided n approaches to infinity. If n is finite, then the statement is correct towards the central portion of PDF. Towards the tails, it may not be that accurate. That's why the name central limit theorem. And this is true regardless of the distribution of yi. So regardless the distribution of yi, the linear combination of normalized IID random variables leads to Gaussian distribution. That is what is central limit theorem. Let us discuss certain important properties of Gaussian random process. Suppose if we apply the Gaussian process xt to a linear filter. I draw it here. Suppose you are applying the Gaussian process at the input of a linear filter or LTI system with impulse response ht and the output is yt. Then in this case, if the input xt is a Gaussian process, the output of the filter is also a Gaussian process. That is, yt is also a Gaussian process. This is one important property of Gaussian random process. Secondly, if you consider the Gaussian process, suppose we have so many functions, sample functions of Gaussian process, and we are sampling, say, at time t1. At time t1, we have xt1. Similarly, at time t2, we have another random variable xt2, and so on. At time tn, we have the random variable xtn. In this scenario, all these random variables xt1, xt2 and xtn are jointly Gaussian. This is second property. It means the random variables obtained at the time instance of t1, t2 and dash dash tn, all of them are jointly Gaussian random variables if the process happens to be Gaussian process. Now we go for third property. Suppose xt is a random process and we have random variables xt1, xt2 and xt1 which are obtained at the time instance t1, t2 and so on. And if you take correlation function, that is expectation of xtk minus mu 2k into xti minus mu 2a at two time instants. And if this correlation function is 0, then these random variables are statistically independent. This is the basic definition of statistically independent random variables. Elsewhere also, same thing is adopted here. So if you consider the Gaussian random variables at different time instants and take correlation function, if it is 0, then these random variables are statistically independent. And the final property is, if a Gaussian process is wide sense stationary, then the process is also strict sense stationary. We know in the strict sense stationary, the probability distribution is same for all random variables. In wide sense stationary, the mean value is time independent and the covariance function is depending on difference of time. So in wide sense stationary, the mean value is not dependent on the time and covariance function depends on the difference of time. In strict sense variation, strict sense random variables, the probability distribution is same for all random variables. But in the case of Gaussian process, if it is wide sense stationary, then the process is also strict sense stationary. This is one important property. Now in this video, we defined Gaussian random process. We have written the equations in terms of matrices and we understood what is Gaussian random vector. We also defined the joint PDF for the Gaussian random vector and we also understood what is normalized Gaussian distribution and we've seen its diagram also with PDFs. And then we also calculated the covariance function of Gaussian process and then we defined the famous central limit theorem and then we discussed some important properties of Gaussian process.